All right, let's get started. Lesson 2, historical models of the atom. In this lesson, we are going to focus on the historical models that have been developed for the atom over the years in order to try to explain what the atom looks like and how it works. Our story begins about 2,000 years ago with the Greeks. The Greeks at this time were very curious and interested in what matter was composed of. And so the Greeks developed two ideas. One of those ideas was led by a man named Aristotle. Aristotle and his followers believed that all matter was composed of base elements that were earth, water, fire, and air. And if you took those base elements and mixed them together, they were composed of all of the materials or matter that the earth was made out of, as well as the universe as a whole. The other idea proposed by Democritus and his followers believed that matter was actually composed of very tiny objects called atoms. What Democritus believed is that if you took a piece of matter, you could divide it and divide it again and divide it even more. And you could keep on dividing it until you got to a point where you reached a particle of matter that can no longer be divided. At that point was called the atom, or he called the atom. The word atom comes from the Greeks, meaning that it was a piece of particle that could no longer be divided. It was indivisible. All right? So these were the two ideas that were proposed by the Greeks. The four-element idea by Aristotle, the atom idea by Democritus. Who won the argument? Aristotle did, mainly because of his popularity. So Aristotle won this argument, and for thousands of years, the world believed that Aristotle was correct. No one really bothered to investigate these ideas further. All right? So what I'm going to do is draw in this first box a picture of Democritus' idea of the atom, his model. So essentially, again, you took a piece of matter and you could divide it millions of times, and eventually you get to the atom, which can no longer be divided at all. Now, Democritus believed that atoms came in different sizes and shapes. And so what we're going to do is draw those. So for instance, it could be spherical, but that these were solids. They could not be broken down at all. We could have maybe, let's do a triangle. Again, different shapes and sizes. Box. But the point was is they were solid and that they could not be divided any further. All right? Now, this idea of Democritus is not going to be more or less resurrected until a man named John Dalton and a group of John Dalton followers about in the 1800s. Okay? Now, John Dalton's going to come and he's going to say, hey, wait a minute. I think Democritus and the early Greeks that followed Democritus were on the right idea. And through some experiments and looking at some data that John Dalton was looking at about atoms or about what matter was composed of, he came to the conclusion that really matter is composed of atoms. So the idea of atoms is going to come back now with John Dalton. He's going to propose some ideas that I want you to know about his theory about the atom and the model of it. First of all, the elements are made up of tiny spheres called atoms. All atoms of an element are identical. All right? So at the time, now, there were these objects that were being called elements, such as carbon, nitrogen, oxygen, fluorine, chlorine, those kind of things, and that these real elements were what matter was made up of. But what these elements really were were really atoms, okay? And that's what he was looking at them. So all atoms then were identical for a particular element. So you had carbon atoms that made up the element carbon, all right? He also proposed that the atoms are given of a given element are different from those of any other element. So he's saying that carbon atoms are different than oxygen atoms, all right? He also said that atoms combined in small fixed whole number ratios to form compounds, right? So like, for instance, oxygen atoms and hydrogen atoms got together and they formed a compound of water that were in a fixed ratio of 2 to 1, all right, which we've already talked about. He also said that atoms cannot be divided into smaller particles, all right? So these were the ideas of John Dalton. Now, some of these ideas are correct, some of them are wrong, all right? So I'm going to highlight the correct ones, all right? First of all, atoms are tiny spheres, all right? All atoms in an element are identical. That is incorrect. But atoms are different from those of other atoms of an element. In other words, carbon atoms are different than oxygen atoms. And atoms do combine in fixed whole number ratios to form compounds. He was correct about that. He was not correct about atoms cannot be divided into smaller particles. So these are the three ideas that John Dalton got correct. Essentially, John Dalton's model could be drawn simply like this. It was a solid spherical object that could not be broken into smaller particles at all. So we're trying to make a solid sphere here. We could draw that in. All right. Soon, a man named J.J. Thomson comes along. Now, J.J. Thomson is going to further investigate this idea of atoms. But his model of the atom is going to come about through an experiment that he's going to conduct, okay? And we're going to fast forward in your notes to basically in your notes, it should be on page 11. And we're going to look at J.J. Thomson's experiment that's going to further change our understanding about what the atom looks like in a new model that's going to be developed by J.J. Thomson. So what did J.J. Thomson's experiment look like? Well, what he did is he took what it was known as a cathode ray tube. This picture here shows what a cathode ray tube looks like. It's essentially a glass tube that contains two different metals in it. A cathode metal and an anode. The anode and the cathode are both connected to a power source, like a battery, for instance. And what happens is when he turns on this battery source or energy source, there is a beam that is developed that is known as a cathode ray. Now, this cathode ray is green looking, okay? Now, this cathode ray was actually discovered long before J.J. Thomson, but no one could understand what this cathode ray really meant or what it was until J.J. Thomson. So J.J. Thomson began to explore these cathode rays and wanted to know a little bit more about them. And so he set up his experiment using a cathode ray. He connected both the anode and the cathode ends of the cathode ray tube to a battery source. He turned it on, and he indeed got the cathode ray. All right? We can look at that in your notes. by this graphic representation, which we'll look at here a little bit closer. So here is the cathode, here is the anode, and both is hooked up by wires to an energy source. And a ray is going to be developed, okay? And that ray is going to hit a screen, okay? There's a screen here. And that ray will hit there and create an image on that screen, okay? But again, this is known, this ray here that we see is green, is called a cathode ray. Now, what J.J. Thomson is going to do that is so unique is that he's going to use magnets. He's going to use a positive magnetic field and a negative magnetic field. And he's going to place those two magnetic fields up against that cathode ray. And what's going to happen is something that he didn't expect, is the cathode ray is going to bend towards the positive magnetic field and repel against or away from the negative magnetic field. What J.J. Thomson concluded is that the cathode ray, this ray, is really negatively charged. Okay, so negatively charged. Okay, he's further going to realize that this ray is not really a ray of light, but a ray of particles that are negatively charged. He's also going to realize, which is important, is that these negatively charged particles are extremely small, much smaller than the atom that John Dalton proposed. All right? And so you can see this as a real life presentation here. You have your cathode and your anode. You see the cathode ray, the green there, and you got a magnetic field that is going to be positive. And the negative magnetic field is going to be up here. And so this beam bends towards the positive field and away from the negative field. And this gave us evidence that this beam of light is not, or this beam is not really light, but a ray of negatively charged particles. Now, J.J. Thomson is going to call these negatively charged particles corpuscles. All right? They are later going to be known as electrons, and they are much smaller than the atom itself. Okay? So this is essentially J.J. Thomson's experiment. In a nutshell, J.J. Thomson is going to basically prove that the atom is composed of electrons. He discovered the electron. So cathode rays are really electrons and not light. So we learn these ideas about the atom from J.J. Thomson's experiment, is that the atom is made up of subatomic particles, namely right now electrons. Eventually the proton and the neutron will be discovered. He also realized that J.J. Thomson's model was wrong and that a new model needed to be proposed. And so J.J. Thomson is going to propose a new model of the atom. So let's go back to our table here and look at J.J. Thomson. So again, J.J. Thomson is going to discover the electron with his experiment. He's going to call the electron corpuscles, but later we just refer to them as electrons. Now, his model is going to look like this. He's going to believe that instead of the atom being solid, that it's no longer solid. Instead, the atom is still going to be spherical, but it's going to be composed of negatively charged particles that are going to be randomly distributed throughout the atom. And those negatively charged particles are electrons. Now, he knew that the atom overall was neutral, and this is very important, that he knew that it was neutral. What that meant is that there was a balance of positive and negative charge. So if the electrons are negatively charged, he also believed that there must be something positive in the atom in order to balance out the negative electrons. And so what he theorized is that the electrons were basically surrounded by an ooze of positive charge. This was an ooze that was positively charged. Now, he's going to call his model the plum pudding model, and this is why. Plum pudding is made up of plums that's embedded or surrounded by a matrix or an ooze of pudding. All right? And so if you can visualize a pudding, it's kind of got this solid look to it, but it's kind of more of a liquid matrix ooze. It's not completely solid. And embedded in that matrix of solid positive charge is going to be these plums, which are represented by electrons. And so we get the plum pudding model by J.J. Thomson. All right? So our understanding of the atom is becoming a little bit clearer now with J.J. Thomson. We now know that the atom is not small or not solid. It can actually be divided into smaller particles known as subatomic particles, and one of those subatomic particles is now the electron. All right? So what we're going to do is we're going to stop here. This is going to be the first part of Lesson 2, the lecture video.